Ciao a tutti.
Okay. So good morning, everybody. Thank you to be here. Thank you to all of the attendees, to our speakers, to be here today for another edition of the BEPA Battery Startups Launch. So this webinar is part of a monthly series where we have the opportunity to listen to 5 startups developing technologies and innovation in the battery space. This edition will see 5 startups that are Imagy, Solvionic, GES, Sencron, and Novak. And so I won't be too long here because I want to give the floor to our speakers. So just a reminder that the session will be recorded, and yes, so that every speaker will have 10 minutes time, including Q&A session. You can communicate with us towards the chat, but for any questions, you can use the Q&A section on Teams, and also then the speakers will be able to reply to you directly in this section if time will not be enough to reply orally. So let's start with our first speaker. I want to give you floor to Axel Schoenecker, CTO at Imagy. So please, Axel, the floor is yours.
Hey, thank you very much. So just to make sure you can see my slides.
Yes.
Yeah. Okay, perfect. Yeah, thank you very much for the invitation. Very happy to talk a little bit about Imagy. Before I start on the company, I would briefly outline a challenge that we all have, and I think we all agree to, and that keeps us busy for quite a while. And that is mainly that I think we all agree Europe needs batteries to do the energy transition and to become net zero carbon society. But we have a big challenge with battery manufacturing. To outline that a little bit, I show you just 2 graphs about material supply. And this graph is a study from the Nordic battery value chain in 2022. We see around 1,200 gigawatt hours battery demand in Europe by 2030. It's a forecast for what's worth. But what we also see is the materials that are needed to bring that in relation to the battery demand. And what we see, especially on the anode side, the announced capacity in Europe is almost 0. So the conclusion from this one will be there will be no anode material to supply the battery chain that we try to set up. More recent study, McKinsey, they have shown in 2025 an overview where are the battery materials produced. China, the big block in it for the anode side, for the graphite production, 93%, 6% rest of the world, 1% North America, and Europe, almost nothing. So there's a big challenge ahead of us if we really think that we can make a battery supply chain within Europe. But on the other side, there's also a big opportunity. And that is where we want to play in as Imagy. Because if you are able to produce the next generation of anode materials in the most cost-efficient way and also with the lowest capex spending to establish the production chain, you're in a good position really to play a big impact in the coming years. And that is what we are aiming for. So to give you a slight introduction on Imagy at a glance, we are a supplier of nanoporous silicon for high-energy lithium batteries. I assume I don't have to explain here in this gremium what silicon can do to the energy density in batteries, and that is entering the market, next generation material. I think that is all agreed and all fine. What we are today is we are a team of above 40 engineers and PhDs in material science, in electrochemistry and engineering. So we do actually two things. We are a material developer. We build our equipment to produce the material, and we also have a test facility to make batteries and to demonstrate the performance in-house. We are located in the Netherlands near Amsterdam. The company itself was founded in 2019, but the team that I'm talking about has worked on silicon crystallization since 2000. So we worked in different fields in solar and thermoelectrics. We have developed different materials for different applications in the past. And since 2019, we are focusing on porous silicon for lithium-ion batteries. So what is the key technology that we are using? First of all, on the left picture, you see what we call the casting machine. That's the crystallization machine. Our technology is based on upgraded metallurgical grade silicon as input material. And that is a big difference to silicon carbide composite materials that are out there, like Group 14 or Sila nanotechnology. They depend on silane as an intermediate product, which is difficult to scale, very expensive, and also to establish, let's say, a good value chain in Europe is actually non-existing. In our case, we use a metallurgical silicon that is produced in Europe, for example, by companies like Ferroglobe or Elkem. So we have quite a good supply chain here in Europe. And what we do is we melt it again, and we crystallize it in a special technology with a rapid crystallization. And that allows us to produce these sort of flakes that you see on the middle picture. And in these flakes, there's a silicon nanostructure already built in. So the last step we do is we mill these flakes down to a porous silicon powder. And that is what you see in the right graph. That is a particle that is a typical particle size of 5 micron. So compatible with, for example, graphite that is used in anodes. And this material can also be used in water-based slurry processing, in a coating on the equipment that is existing in battery manufacturing lines. But of course, silicon has a big challenge, and that is the swelling that silicon undergoes when it lithiates. And that is why we built in this nanoporous structure. The silicon, each particle has channels around 200 nanometer in diameter that go all the way through the particle. And this inner porosity can be used like a sponge to compensate for the expansion of the silicon. And that allows us to make stable particles that don't break and that cycle very well in lithium-ion batteries. So we have a couple of advantages here. We have a material that has demonstrated that it works. And we have a supply chain that is completely based on metallurgical processes. So we can actually scale with this sort of equipment in a very natural way. Investments are roughly a factor 10 lower per kilogram than, for example, for silicon carbide composites. And also the manufacturing cost on industrial scale is much lower than what can be achieved with silicon carbon composites. The other challenge that everybody talks about is, of course, if you work with pure silicon, it's a limited lifetime, the cycle life that is achieved in batteries. And in this field, we are actually progressing very fast at the moment in cooperation with electrolyte partners. And we have tested a lot what we call standard formulations. That is just what you see in the blue lines in the graph here, where typically achieve cycle lifetimes in battery of around 200 cycles maximum. These are the electrolytes that are developed for graphite and graphite anode material in combination, for example, with NMC cathodes, and they are limited. If you change to advanced electrolytes, that is something that we started roughly 1.5 years ago. And the first iteration went up to 250. And today, actually, we are working with two classes of slightly different electrolytes that both have cycle lifetimes above 500 cycles. In a battery that is where the anode is based on 85% silicon. So it's a pure silicon anode with some conductive carbon and some binder involved in it. And these are test results against NMC 811 in 3.5 milliampere hours per square centimeter cell. So actually already cells that are close to industrial applications. Also, these advanced electrolytes, they have advantages in gas formation, so they are very benign, and they can be applied in batteries. So what is our journey to bring this product to the market? Of course, we focus a little bit along the cycle life requirements in the different markets. So we start with drones. We are in consumer electronics. And of course, we see the electric vehicles somewhere in the future as the big market where we are heading towards to. How do we do that? I've said we are a material producer, but we realize that we have to demonstrate the performance in batteries to be accepted on the market. We have a battery lab, so we can make coin cells and pouch cells to a certain limit. But what we have done is we went out and enabled cell manufacturer both in Europe and in China that they know how to work with our material, that they can make slurries, that they can make 100 meters of coatings, and they can make series of cells. And that is what we use to supply cells via these manufacturers to drone or consumer electronic projects at the moment. So in the left picture, you see a selection of pouch cells for different applications with different dimensions. And the right one shows a project where we made 1.5, or we let make 1.5 ampere hour cells, around 300 watt hours per kilogram by a European cell manufacturer in this case. So what is our target and what is our position in the world? We want to empower our clients with next generation battery performance. We are a producer of a nanoporous microsized silicon. We produce this on a pre-industrial pilot. We have the capability at the moment to produce roughly a ton per year, and we are upscaling with the existing equipment to around 50 tons per year in the next 2 years. We are prepared to scale this material manufacturing with a technology that is potentially the lowest in CapEx. So it means if Europe really wants to produce the anode material that we need in the future, we have technology available to do this very cost efficiently and outperform the existing graphite manufacturing. We also expect that we are very low in manufacturing costs, and the process itself is environmentally benign. We actually only need electricity, preferably from a renewable energy source, of course. So we see silicon as a big opportunity for Europe, and we position our company in a sweet spot to realize that. And with that, I thank you very much for your attention.
Thank you, Axel, for your presentation. Now we have 1-2 minutes for questions, because we have then to move to the next speaker. I see there are some questions in the Q&A section, so and then you can of course reply yourself if we don't have time to reply to everything. But so first question is if why the cell shows increasing capacity in the first 50 cycles?
That is something that we see quite often. That's due to the formation that we use. We use a formation cycle with C/10, C/5, and during cycling we go to C/2. These advanced electrolytes have then they lose a little bit of capacity, and that is regained in the first 10, 20, 30 cycles to stabilize. So it's a more artificial effect due to the transition in the cycle velocity.
Thank you, Axel. I will unfortunately have to move to the next speaker, but I see that there are other questions in the Q&A section. So if you should be able to see these questions and reply now, like in written form.
I will do that, and also my email is shared. So if somebody comes later on with question, happy to answer them. Thank you very much.
Thank you. So our next speaker is Sebastian Fantini, Head of Innovation and Business Development at Solvionic. Hello, Sebastian. I will share now your presentation. Okay. Okay, please, Sébastien, the floor is yours.
Hello, thank you, Elena. Thank you very much for the invitation. Hello to everyone. So yeah, we'll be speaking about our range of electrolyte solulite, which is compatible with lithium metal and which is used as the solid-state battery enhancers. Next slide, please. So as the menu, we will start with a short introduction. Then as a starter, I will show you some evidence of solulite compatibility with lithium, and then we will go into the main course, which is the solulite that is used as a solid-state battery performance booster, and then we will conclude with a short dessert. So please, next slide. Thank you so much. So yes, Solionic is a company focused on a specific chemistry of ionic liquids, and this is our roadmap to industrialization. And as you can see, we are now ready for pilot production. And what we would like to do according to this timeline is to be ready for our current clients, to be ready when they start mass production. So at the moment, we are ready for their pilot scale activities, and the next step would be the installation of our industrial line, which will be based on continuous flow technology, the same technology that is developed at the pilot line, and that those industrial lines will be also developed according to the market needs. So the good thing is in the continuous flow technology is the fast possibility to install and duplicate the lines, so that we can adapt our production capacity to the client's demand and market demands. Next slide. So on the market that we are on, it's not only we are not only on the market of energy storage, even if this is the main one that we have, but we also develop specific formulations for other markets, such as lubricants, for example, in some niche markets, such as space applications. And of course, ionic liquids are also used as solvent supports for different kind of chemical processes, such as catalysis or cellulose dissolution, for example. Next slide. So now we start with the solulite lithium compatibility. So here you can see a full cell that is mounted with an LNMO cathode, which is provided by a Topsoe company, together with a lithium metal anode, which is provided by another company who produces lithium metal anodes. So you have the cycling condition from 3.5 to up to 5 volts, which is quite high voltage. Here we only show the C/2 cycling steps, but there is also a formation step that is not shown here, but formation step is kind of regular compared to state-of-the-art electrolytes. So 100% depth of discharge and room temperature cycling. So you can see here that the cycling stability of our electrolyte with 2 different solulite formulations is quite good. And there is still a way to improve that, as it is shown from moving to E623 solulite up to E712. There was an optimization here. We are also using some ionic additives. So this is a completely ionic based formulation, which shows the outstanding cycling stability with lithium metal. Next slide. So this electrolyte doesn't work only with lithium metals. So just to tell you, we have also experimental evidence that can be shown outside of this presentation on NMC 811 graphite, which for which we achieve a very good cycling stability. High voltage cycling stability also with LNMO graphite. The example that we have just seen was on lithium metal LNMO. We have much better cycling stability, obviously at elevated temperature, since we are using full ionic liquid electrolytes. One of the shortcomings is the low performance at high C rate when room temperature is used. This is due to the bit higher viscosity of our electrolytes compared to state of the art. Next slide. Sorry, but what? Yeah, the previous one, please. Previous one again. Yeah, thank you. So the what is interesting here today is the compatibility of our solulite with lithium metal anodes, and so how can this be used in solid state batteries composed of lithium metal anodes? So next. So this is the core of the presentation. Next, so the main course. So here you have a comparison between different concepts of solid state. So to improve the all solid state batteries, for which we all know the issues of interfaces, compatibility, for example, or the several weaknesses of all solid state lithium batteries. So we go through, or people who is developing a solid state battery go through different kind of hybrid concept, from all solid state to almost solid state, where you can see that the interfaces are weighted with some liquid, down to semi-solid state batteries, another concept again, where you can use nanode jellified by a liquid, the electrolyte that is jellified by a liquid, or the cathode that is also jellified by a liquid. So here we have a catholyte in the cathode, or we can have a nanolite in the anode. So one of those three components, the anode, the separator of the cathode, can be weighted by a liquid, or all the three together, which gives you the concept of semi-solid state batteries. And then we have the liquid one, the lithium-ion batteries, which is the full liquid electrolyte system. So adding a liquid to your liquid to your solid state improve the performances, because it enhances the charge transfer at interfaces. But the problem is that the more you add liquid organic electrolytes in the system, the more you decrease the safety aspect of the solid state, which is one of the reason why we are working all on solid state. So next slide. So you can.
Sorry,
you can...
Sebastian, to interrupt you. I wanted just to tell you that you have 2-3 minutes left. So just also for questions.
Yeah. Okay. Thank you. So you can see here on the next slide. The next slide, please. Yeah. So when you add the liquid part on your system, you can see that you can improve the solid state properties, which is weak when it's completely solid. So you improve the ionic conductivity, you improve the interfaces contact when you add the conventional liquid to the solid state electrolyte. But the problem is that you decrease the safety aspect. Next slide, please. But when you use the HYNEC liquid instead of conventional liquid electrolyte, next slide, please. Then you still improve the conductivity and the interfaces contact, but without losing any safety aspect and any high temperature ability to work with solid state electrolyte. So the next slide, please. So as the end of the presentation, next slide, to conclude, we have seen that our solubylite chemistry is compatible with lithium metal. It's also compatible with high voltage materials, and this is great since it can improve in a sense the solid state batteries performances without losing any safety aspect. So next slide, I will thank you for the attention of. Thank you very much, everybody, for your attention.
Thank you, Sébastien. Unfortunately, I have to give the floor to the next speaker, but as I said before, to the attendees, please drop your questions in the Q&A section, and as a speaker, you should be able also to reply in the meantime. Thank you. So our next speaker is Ilaria Pucher, Head of R&D at Green Energy Storage. Please, Ilaria, the floor is yours.
Thank you. I'm going to share my screen. You should be able to see it, I guess.
Yes, perfect.
Okay, great. Okay, so thank you everyone to listen to my talk. I'm Ilaria Pucher, Head of R&D, and I'm pleased today to talk about green energy storage. Green energy storage is an innovative small enterprise based in Trento, in the north of Italy, that develops redox flow batteries. The mission of the company is that of reshaping the energy transition. And our motto is, well, today's storage batteries last hours, tomorrow's will need to last days. And so the goal is to build that tomorrow. And so with our green and sustainable energy storage system, we would like to build the future of renewable energy. So what are redox flow batteries? The redox flow batteries are batteries in which energy and power are decoupled. And therefore they are independently scalable. So in particular, energy is defined by the volume of the usually liquid electrolytes in which redox couples are dissolved, while the power is defined by the cell area or the stack size where actually redox reactions occur. In addition, redox flow batteries usually have a very long cyclability, usually more than 10,000 cycles. They do have a pretty good energy efficiency, more than 80%, and they don't usually need thermal management. Also, they have a competitive levelized cost of storage, LCOS, when we are in the field of long duration energy storage applications, so LDES. So all these characteristics make redox flow batteries a perfect candidate for long duration energy storage applications. But what's long duration energy storage? Well, it's energy storage with a discharge duration that is more or less above 8 hours or so. And what are the requirements? Obviously modularity, and we said that redox flow batteries are modular in the sense that energy and power are decoupled. And they can span from a few kilowatt to large systems, so megawatt scale. In our case, but also in flow batteries in general, they can respond then to the needs like in the EV charging stations, for example, residential applications, industrial storage systems, but also grid scale systems, also coupled with wind and solar farms. Green energy storage is part of the IPCEI community. in particular the second IPCEI batteries called Yubatin. We have a project with a budget of 62 million euros, more or less, that started in 2021. The project goal is that of developing this innovative flow battery from R&D to first industrial deployment. And we are actually right now testing the first prototypes and are going to be ready for field tests next year. Okay, but what's so innovative about our redox flow battery? Well, in our flow battery, we only have one liquid electrolyte. Usually there are two liquid electrolytes. In our, there's only one. So we only have to take care of one supply chain. So only for one electrolyte. And this is manganese, which is dissolved in an acid, more or less. On the other side, instead, we have hydrogen. Hydrogen evolves, is generated during charge, then is stored in a tank, and it's consumed during discharge, like in a reversible fuel cell. So in particular, here we can see a drawing of the charge process. So here see when we go from -2 to -4. At the analyte side, we generate hydrogen and we store it for the discharge part. And then during discharge, we consume the hydrogen, so we end up with an empty tank, and the manganese solution goes back to a liquid and transparent solution. So where are we now? Here is the situation of today's situation, more or less. So we are testing stacks on the right-hand side. At the bottom, you can see one of the stacks that we are testing right now. The electrolyte is stored in the tank that you can see here at the top. While on the left-hand side, you can see the hydrogen system part with the balance of plant. We are actually going to test a stack that is 4 times the power of this stack in about a month. And based on the size of that stack, we created some realistic rendering of how the final power module will look like. And this is the power module, the final power module that we have in mind. I'm sorry, this is actually an old rendering, but the new one is about to become public in a couple of months, so I can't publish it now. But anyway, this is a realistic view of how the power module will look like. It's a more or less 10 kilowatt stack that can these stacks that can be piled up in a rack that's called skid, and this can be containerized in open top containers, either 20 feet or 40 feet containers, depending on the need. And all these skids can be used to actually make a plant. And this is the simplified rendering of a 1 megawatt, 10 megawatt hour plant that we have in mind. On the left-hand side, you can see all the skids in this building here. But on the right-hand side, you can see the hydrogen storage tanks at the bottom right. Then you can see the plant management unit in the middle, and then the electrolyte storage silo at the top. We can then go further, and we actually have here a rendering of a 10 megawatt plant with a 10 hours storage duration. You can see all the skids here on the left-hand side in this building where the power units is located, with all the skids and the auxiliaries. We have a plant management unit on the right-hand side with also the hydrogen storage tanks and the electrolyte storage silos here. And to conclude, I would like to show you a nice qualitative, let's say, image of the footprint of our 10 megawatt, 100 megawatt hour plant. Compared to an 8-hour megawatt wind farm that is located, it's a real farm that is located in Verona. It's more or less 50 kilometers south of our facilities. And we can actually see that the storage plant could very well fit inside the wind farm without the need of additional space, which translates in one, that we will be able to achieve our mission of building the future of renewable energy.
Sorry,
And
I have to interrupt you just because there are 2 minutes left.
Yes.
So for eventual questions, yeah,
And I'm
just to
done.
let you know. Okay, sorry. Perfect.
Thank you.
Thank you, Ilaria. And yes, I think let's see if there are some questions. I think there is a question from 2 minutes ago. What is the total cost of ownership of the Redox Flow battery compared to LIB? And what is the targeted storage time? More than 8 hours.
Yeah. So long duration energy storage is basically the segment that we are looking at. And so I'll start with that question. This is going to be a little different compared to lithium-ion batteries. So we are going to focus on long duration energy storage. So 8 hours, but then they can be 10, 12, 15, 16, 20, 24, and even days. What about the total cost of ownership? Well, the metric that we use is the LCOS, so the levelized cost of storage, which takes into account not only the capital costs, let's say, but also OPEX, maintenance, cyclability, and so on. And I can say that at the industrial side, Redox Flow batteries are really competitive, and they can achieve the cost of lithium-ion batteries for durations that are above 8 hours. That has to be stressed. So below 8 hours, Redox Flow batteries are not that competitive. But above 8 hours, when you get to mass production, they can really be competitive. Yeah.
Thank you again, Ilaria. And yes, please feel free to reply to other questions in this Q&A section.
Thank you.
Thank you. I will now move to our fourth speaker, Nuri Sensoy, Head of Data at Cenkron. Please, Nuri, the floor is yours.
Thank you. Thanks so much. I think my screen is shown, right?
Yes.
Thank you. I am Nuri from Cenkron, Head of Data. Today I will represent my company, Cenkron Digital. What we are doing, I'm trying to explain what we are doing. First, I would like to tell about our mother company. Is the Enerjisure team. Our mother company is a joint venture company of the E.ON and Sabancı Holding. Sabancı Holding is the biggest holding company in Turkey. We start to 1996 our operations in Enerjisure team. More than 30 power plants with more than 4 gigawatts in 6 different technologies. We are managing these power plants. And today, and for many years, we have been managing this large structure from a central point with our own softwares, in-house softwares, in our central system, located in our headquarters in Istanbul. This headquarters in Istanbul, we have some room we are calling the remote operation center. We call this room as a Cenkron. We are, for many years, we are managing our power plants in this room, in Cenkron room. And with this idea and with this stall, we create our new company, our new spin-off company, Cenkron Digital, to start to give as software as a service to the other companies with this new brand. And we establish our new company, Cenkron Digital. Where we are now today in Cenkron Digital managing the power plants in different kind of countries, more than 15 countries in 4 different continents, more than 8,000 megawatt capacity, more than 40,000 OT assets, and more than 50 critical sites. What we are doing, mainly what we are doing, we have 2 different products in our sites. One of them is the OnePact, and other one is the CyberPact. In OnePact, we are managing the power plant end-to-end with the end-to-end solution in our system, starting from the investment plan to the end of the commercialization sites. With the OnePact, we are managing whole life cycle of the power plants, of course, containing the battery storage system, and I will explain about that. In the CyberPact, we are giving a service, OT cybersecurity service for the critical components of the assets. Today, I will mainly focus on the OnePact because the OnePact site is much more related with the battery storage systems. Last month, we realized the OnePact EMS. Of course, you heard many times of the EMS keywords in different kind of companies, different kind of events. Everybody using the EMS content in different kind of contents. But in our company, in the under of our brand, we redefined the EMS concept. We defined OnePact EMS, and the OnePact EMS, there are 4 different kind of modules. These are the OnePact Monitor, OnePact Predict, OnePact Feasibility, and OnePact Monetize. We believe that with these 4 different kind of module, we are managing the power plants, especially containing the battery storage system, especially the hybrid power plants containing the battery storage system. We are managing end-to-end, starting from the investment planning, the monitoring, performance monitoring of this power plants, the battery storage system, and the commercialization of this power plants, especially to the market operator side and the transmission system operator side. And we design this structure, this software with these 4 different modules. Of course, we have limited time and it is hard to give the deep detail of this module, but mainly we are starting with the feasibility side. In the feasibility side, we have an optimizer developed by in-house software team. With this optimizer, we are giving the feasibility report, and we are preparing the feasibility report of your battery integrated power plants to increase your ROI, increase your net present value, increase your cash flows. And we suppose that we will use this optimizer in the monetized side. It means that we are planning your power plant. Also, we are using the same structure in the real life. Because of that reason, every module is talking with each other. It is very important, and it is most powerful point in our sites. Every module is talking with each other to create maximum efficiency and maximum revenue for the asset owner, especially having the hybrid power plant containing the battery storage system. We have different kind of real world impact in each modules. In monitor sites, you can manage your power plant in the only single monitoring platform as a flat management. You can increase your efficiency. In the predict side, we are making the predictive maintenance services to the asset owners, especially having the battery storage system. We can increase your uptime. In the feasibility side, it is very hard. Everybody we are talking with our customer in Europe and different kind of countries. Everybody have a question: how much capacity in battery storages I have to put my site? It's a very important question because determining this optimal capacity is very hard question, and it's a very complicated question. With our feasibility product, we can develop your investment plan with feasibility, and we can increase your return of investment with your developing site. In the final end, the monetized site is the last point actually. We are managing and we are planning our power plant. At the end of this process, you have to integrate your power plant, or you have to integrate your battery storage system to the commercial sites. With monetized sites, you can directly integrate to the market operator site and the transmission operator site to increase your operations more faster, and of course, increase your revenue getting from the hybrid power plants containing the battery storage system. Our most important point of differentiation is that we see ourselves not as a software company. We are the software company, we are company providing services to our customers, especially specialized in the energy know-how, energy domain. This is most important point of us is we are not just developing the software. We are developing software coming from the knowledge, from the business know-how, coming from our mother company's knowledge, especially having 6 different technology containing, of course, a battery storage system. There is little bit two important news in our site. I put just only one image from that. This image is our Enerjisa, our mother company's site. The first battery project in Turkey to receive energy minister approval in Turkey is managed by end-to-end with our application. Is what our one pack is a very huge information, a huge news for us, because it is the first battery storage system integrated to the transmission system approved by the energy ministry, and this battery storage system managed by end-to-end with our one pack platform. The last news I want to give this news. It's very important for us again. I would like to share this news because we are named the newcomer of the year at in the Storage Award this year. This has given us significant motivation as we move forward. We are trying to rewrite the rule of the battery storage system, management of the battery storage system, integrated hybrid power plants with our new idea about the EMS, one pack EMS. Thank you for listening to me. I'm Nuri Şensoy, Head of Data. I am really appreciate to listen to me. Thank you.
Thank you, Nuri. I see a question for you. Do you see more interest in your product from the BESS operators, or at smaller scale like industrial site storage, or even private energy traders?
Of course, this is scalable to different kind of. It is about we have. I said that we have 4 different modules. These modules is not always the necessary to use for all projects. Sometimes the project is not directly integrated to the, for example, the TSO and or the market operator. You have to move these modules and you have to continue with other kinds. Of course, we have this functionality.
Thank you. For the moment, I don't see other questions in the chat, but please feel free to drop your questions even during the next presentation, and you can also reply in the Q&A section. Thank you again, Nuri.
Thank you so much, Anna.
So our last speaker of today is Mattia Colalongo, R&D scientist at Novak. So we are running a bit late, but we should be able to finish a few minutes later. Please, Mattia, the floor is yours.
Thanks, Anna, for the introduction. I hope you can hear me go in slideshow mode. All right. So yes, I'm Mattia. I'm R&D scientist at Novak. Today I'll be representing the startup company. Novak was founded in 2020 in Modena, in Italy, and we have knowledge on energy storage materials, and we develop high performance EDLC or supercapacitors and hybrid supercapacitor hybrid systems. To give you more information about the company, the team has a variety of expertise, from PhD in electrochemistry or electrode and cell engineers, system integration engineers for BMS development, and simulation engineers. We work on the materials, we develop the cells, and eventually the battery pack, depending on what the customer needs the most. In 2022, it was just a laboratory research line. We could produce like 30 cells per day in terms of coin and pouch, but nowadays we have commissioned thanks to the last round of investors, we have a pilot manufacturing line, which will give us the possibility to produce more than 200 cells per day. And this is only in of course, in each sector, from materials, cells, and pack, we have different expertise. As I told you before, we source the material, we prepare the slurries, and then we manufacture the electrode. by ourselves, thanks to our line. Then, of course, we work on the cell assembly. We characterize the cells with potentiostat and then cyclers. And then if the cells are okay, they go in the pack. And then we characterize also the pack. And we also have our own, because our supercaps and non-batteries, we have our internal management systems. So the chemistry we work on the most are the EDLC or the supercapacitors. Here we are much more experienced. We produce these supercap already. Of course, the characteristics are simple. They can go up to 1000 C. They can reach 500,000 cycles, and they can just work down to minus 40 degrees, so very low temperatures. And these are perfect for a combustion engine cranking to start up the engine, or as a power buffering most of the times. Hybrids are a new technology we're trying to develop. These are our TRL is lower, but it's still in the R&D section, not really in development mode. But of course, we reach a lower C rate compared to it can handle lower C rates compared to the supercap, but much higher than the batteries, and also the life cycle compared to the battery is much higher. Compared to the supercap, we get double the capacitance, and this is great for grid support or UPS eventually. Now, the difference between an EDLC or a hybrid supercap is pretty simple. For an EDLC, we just use activated carbon at the positive and at the negative electrode. These are symmetric systems. But for a hybrid, we just change in the anode. Instead of the activated carbon, we use LTO, which is a known electrode that sustain high C rates. So here is an example in electrochemistry-wise, the two systems. Of course, at same on the left, you see specific capacity under a specific current, or C rate. It's a similar way of expressing this data. At the same C rate, we see that the hybrid supercap has higher capacitance, but at lower C rates, the hybrid can deliver much more energy than what a supercap can do. This is a great technology which is in between supercaps and batteries. Here there's just an example of discharge curve from high voltage to low voltage of the supercap against the hybrid, and you can see that has a much higher energy to store. Now, Novak is a company that has also funded, involved in a funded European project. For example, Met Supercup. We have like 2 million to use. It's a way to establish a traceable measurement and characterization framework for supercapacitors, which is something not really available in Europe. We know pretty well batteries, but supercaps don't have this metrology developed, at least for I think the European network. There's another funded project for a hybrid. It's called Inception, and the idea is to develop zinc-based metal anode battery supercap hybrid materials. This is also like a way to sustain this type of technology over time. A few applications of Novak supercapacitors, for example, they've been included in satellites radar. These were used as a power peak shaving in 2024, substituting completely what they were using lithium-ion batteries. They just inserted supercaps. They managed to reduce the mass 41%, and of course gain more cycles compared to what a battery usually can give you, which is around 5K or 10K if we're lucky. And supercaps can work at very low temperatures, minus 40 degrees. The same idea was applied to a combustion engine starter in a truck. This is ongoing right now, and the idea is basically the same. Try to optimize the volume of the system using supercaps instead of, for example, a lead acid battery. These devices are completely safe, okay? They contain no lithium whatsoever. Another use case. This is a market we're trying to shine in the next future, I hope. But we can use supercaps as a UPS. So the idea is a value proposition. One idea is to use these devices to extend, for example, the battery cycles, supporting the power shaping exactly the power peaks of what the grid asks. And then we can therefore reduce the maintenance of the system. For example, if you have like a battery pack close to the supercap part. So this is pretty much everything from me. I try to be as quick as possible to leave like 2 minutes for the Q&A if there is any. So thanks for your attention.
Thank you, Mattia. I'm checking. Yes. I don't see any questions for the moment. Maybe. Yes. Okay. So yeah, I see a question here. What type of electrolyte do you use?
Good question. In in supercaps or a hybrid, for example. Okay, let's say both. In supercap, I cannot say because it's an internal formulation, unfortunately. And for a hybrid, these are lithium Li PF6 based electrolytes because they have to go through a Faradic reaction, and so they need some lithium plus inside. So this is the main difference. But for the supercap, I cannot say. This is fortunately, yeah, company formulation. I'm sorry.
I see
But
another.
you can reach out. You can reach out, and we can try to. After NDA, we can talk about it.
I see another question in the Q&A section. You said there is no Li, but you are using LTO. How is it so?
Yeah, this is true for the supercaps. The no Li was specifically for the application that I showed here. These are just supercaps. And so in here, we don't use any lithium whatsoever. In the application with hybrids, I didn't show any application with hybrids. Of course, you have lithium, and so safety is still a concern. That's absolutely true. I went too quick, but I hope this is clear. This is in this application there is no lithium as we are applying just supercaps, and the same is for this slide. Application for hybrids there is something to still find out, but I didn't show any application yet. I hope it was clear. I don't know if I answered the question.
Okay, we have time maybe. Okay, so yes. So thank you, Mattia. And yes, so we are almost on time. Thank you for all the questions. And yes, as previously mentioned, please feel free to reach out to our speakers. Thank you for your presentations to all our speakers. And just a reminder that we will be sharing with you the recording, the presentations, that we will also host another edition of this BEPA battery startup launch in November on the 24th, and we will be sharing the details closer to the date. So yes, once again, thank you all. I wish you a good lunch if you haven't eaten yet, and have a good day.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye-bye.
Bye-bye.
Thank you.